Alright, so we're going to build off what we were talking about in last class with refraction to talk about thin lenses. So, for starters, just as a basic definition, what are lenses? Well, lenses are devices that focus light through refraction to form an image. So notice here's a situation where I've got a lens and I've got light coming in, and what you're seeing is that light gets bent at this side of the lens, it gets bent again at this side of the lens, and so at the end of the day I end up with an image that's being formed due to that refraction. So for starters, one of the important points that we'll talk about with a lens is the focal point. And so you notice that the focal point here happens to be where the image is forming, and this is what happens when my light comes in as parallel rays. So my light coming in as parallel rays basically tells me that I can act like my image is infinitely far away, and so if I have my object is infinitely far away, and so if I have an object that's infinitely far away, then that's going to create an image at the focal point. All those rays will come in and focus at the focal point. Now, as a general rule, I don't have an object that's infinitely far away. So instead, to figure out where my image will form, then I'm going to care about the focal length. And the focal length is the distance from the lens to the focal point. So whatever this focal point is, how far away it is from the lens is the focal length. And that's a distance that I'll care about in trying to figure out where these images will form. So one of the things I'll go ahead and emphasize now is that there are going to be three distances we talk about: the focal length, the object distance, and the image distance. And all of those are distances that are defined relative to the lens. So the focal length goes from the lens to the focal point. Okay? So because our light gets bent as it passes through the lens, then the light rays are going to seem to come from a point that's either closer to or further away than where they're actually originating, which is why we're going to end up with the images that we have. So the way that the light bends through the lens is going to dictate what kind of image we have. So let's start by describing what kind of images that we can form. So there's basically sort of three sort of sets of categories that we're going to care about in terms of thinking about our lenses, or our images. And the first is it a real image or is it a virtual image? So a real image is an image that can be projected on a screen. So that's produced when rays come together. They come together at some point, and you can set a screen there. A virtual image is an image that you can't put on a screen. So instead, it's an image that's produced by diverging rays. So your rays are actually diverging as they go through the lens, and it looks like that image is being formed on the other side of the lens. So you can't put a screen there, or else you would be blocking the light as it goes through. So what we're going to see is that real images will always be produced on what we'll think of as the image side of the lens. Virtual images will always be produced on the object side of the lens. It's part of why you can't put a screen there. The second category that we're going to care about is, do you have an image that's enlarged or reduced? And this one's fairly straightforward. An enlarged image is simply one that's larger than the object. A reduced image is one that's smaller than the object. So another thing that we'll care about is your image, what's the size of your image relative to the size of the object? Is it getting larger or is it getting smaller? And then the last one is going to be upright or inverted. So sometimes when you form an image with lenses, that image is upright, meaning that your object isn't flipped over. It's oriented in the same direction. The image is oriented in the same direction as the object. If you have an inverted lens, on the other hand, that means that it's been flipped. So your image is flipped over relative to the orientation of the object. So we usually draw our objects as arrows. And so what we'll see with an inverted image is that instead of an arrow pointing up, like our object, the image will be flipped over so that we have an arrow pointing down when it's inverted. So at the end of the day, part of what we're going to care about is, okay, so the object or the image formed by this lens, is it real or virtual? Is it enlarged or reduced? Is it upright or inverted? Okay. All right. So what types of lenses will we deal with? Well, for starters, we can deal with either convex or converging lenses. So these are just two ways of talking about the same type of lens. Basically, what convex lenses do, they're called converging because basically the light passes through them and converges on the opposite side of the lens. So the light gets bent so that it converges on the far side of the lens. Convex lenses have a positive focal length. So we'll talk about several important sign conventions here, and one of them is just going to be what sign do we give to the focal length. And so the focal length is positive if we have a convex or converging lens. That's entirely dictated by the type of lens that we have. We said that there are three important distances that we're going to keep track of. One we've already talked about, that's the focal length. There's f, right, the distance from the lens to the focal point. The other is the object distance, which we're going to denote with a little s. That's the distance from the object to the lens. The other is the image distance. That's the distance from the image to the lens. So here we have here's our object, and it forms this image. Okay? Now, again, we said one of the critical questions that we're going to ask each time is what kind of image am I creating with this lens? And so in this case, if I want to think about what kind of image this is, well, in terms of my first category was real or virtual. And so we said a real image is going to form on the opposite side of the lens as the object. That's how you can put a screen there without blocking the light coming through the lens. So this is in fact a real image. Is it reduced or enlarged? Well, you can see from this that the size of our object, the green arrow, is larger than the size of our image, the red arrow. So this is a reduced image. And then again, is it upright or inverted? Well, the green arrow points up, the red arrow points down. So the orientation has been flipped over, so this is an inverted image. So this particular image happens to be real, reduced, and inverted. The second type of lens that we'll talk about is a concave or diverging lens. And so here, again, what you have is the light from the object comes into the lens, and now it diverges away. And so where these diverging rays seem to connect is actually here. So here you've got where these two things intersect. So here's where your image forms. Again, because this is a concave lens, it's a diverging lens, we said what type of lens it is tells me what sign I need to use with the focal length. And for concave lenses, we have a negative focal length. So there's still the focal length. It's still the distance from the lens to the focal point. We're simply going to give it a negative with our concave lenses. So again, we still have our object distance, the distance from the object to the lens. We have our image distance, the distance from the image to the lens. So here's still our three distances that we care about. And again, in terms of what kind of image this one is, well, so the first thing to notice is if I were to try and put a screen where my image is, that would block the light from going through the lens. So if you put a screen here, this image would never form because basically you'd be blocking the way for the light to go through the lens to form the image in the first place. So this is on what we'll end up calling the object side of the lens rather than the image side of the lens. So this is actually a virtual image. Right? This is not one that you can actually put a screen on and see. Is it enlarged or reduced? Well, again, it's clear to see that the green arrow, my object, is much larger than the red arrow, my image. So this is a reduced image. And then is it upright or inverted? Well, the green arrow, my object, points up. The red arrow, my image, also points up. So they've got the same orientation. So this is an upright image. So using my concave lens in this case, I have a virtual reduced upright image. And so what we'll see is converging lenses can form different types of images. Concave lenses only form one type. So this is what you're always going to get with a concave lens. You're always going to get a virtual reduced upright image. All right, so in terms of the two equations that we'll really work with in terms of working problems with thin lenses, one, there's the lens equation, which relates the object distance, the image distance, and the focal length. And of course, the thing to pay attention to here is that that's 1 over the object distance plus 1 over the image distance equals 1 over the focal length. So this will help. This equation will largely let us figure out where our image is going to be located. Then our magnification equation will tell us a couple different parameters about how our image compares to our object. So notice there are a couple ways that I can calculate the magnification. One is negative image distance over object distance. The other is simply object height to image height. And so again, there are a couple of important sign details that need to be taken into consideration here. So if our light rays originate on the left-hand side of the picture, which is usually where we will let them originate, and so here's our lens, here's the principal axis here. So in terms of signs, we're going to have the side that the light rays originate on is the object side of the lens, and so objects over here will have a positive object distance. If the object happens to be over here, which could be the case if we have multiple lenses, right? When we start putting multiple lenses together, you could have a situation where the image of your first lens becomes the object of your second lens, and in that case, you could have an object that's over on what we would think of as the wrong side of the lens, and in that case, the object distance would be negative. But almost always we're going to have positive object distances because we're going to have our object on the same side of the lens where the light's coming from. Now, it switches with the image. So where the light's coming from is the positive object side of the lens. Where the light's going to is what we think of as the image side of the lens. So if you have an image that forms away from where the light originates, on the other side of the lens from where the light originates, that's going to have a positive image distance. So images that form on the object side have a negative image distance. Images that form on the image side have a positive image distance. So sort of what sign your image distance has is literally based on which side of the lens the image forms on. Now the other detail to keep in mind in terms of signs is if you're talking about your object and image height. Well, above the principal axis has positive heights. Below the principal axis has negative heights. So in our first picture where we had a object over here that pointed up, and we created a real reduced inverted image. So since my image was on this side, that would be a positive image distance. My object was over here, that would be a positive object distance. So part of what this would be telling me is that the magnification would be negative sign times ratio of two positive quantities. My magnification would actually be negative. In terms of thinking about this equation, well, because my image is below the principal axis, right? It's inverted. My image height is going to be negative. My object height will be positive. So this equation gives me that same negative magnification. So this equation we'll use to figure out the magnification of an object. This equation we'll largely use to figure out the location. So just to sort of kind of put all these sign conventions into a single slide to kind of organize them. Your focal length is positive if you have a converging lens or a convex lens. Your focal length is negative if you have a diverging lens or a concave lens. So for starters, just the sign you put, the sign that goes with our focal length is entirely determined by what kind of lens we have. The next one is that the object distance is positive if the object is on the same side of the lens as where the light originates. So you have a real object in that case. The object distance is negative if the object is on the opposite side of the lens from where the light originates. And again, this is only really an issue when you start putting multiple lenses together. So if I start forming an image from one lens and that image becomes the object for a second lens, say like what you might do with a microscope or a telescope, then this becomes an issue. My image distance is positive if the image is on the opposite side of the lens from where the light originates. So again, my image distance will be positive if the image ends up where the light goes through the lens, if it ends up on that side of the lens. My image distance is negative if the image ends up on the same side as where the object, or where the light originates. So again, we often think of this as I have a positive image distance if I'm on the image side of the lens, a negative image distance if I'm on the object side of the lens. And again, you notice that whether I have a real or virtual object, or whether I have a real or virtual image, is literally just encapsulated in, well, what's the sign of the image distance, or what's the sign of the object distance or the image distance. In terms of thinking about the magnification, there's a couple details that I get from that. So we said whether my image is real or virtual, that's an issue of thinking about the sign of my image distance. Whether my image is enlarged or reduced is thinking about the absolute value of the magnification. So when I take the ratio of image height to object height, or image distance to object distance, if that ratio is greater than 1, then I have an enlarged image. If that ratio is less than 1, I have a reduced image. So again, it's a situation of where just looking at the number, ignoring the sign of the magnification, will tell me whether I have an image that's enlarged or reduced. And then paying attention to the sign of the magnification will tell me whether or not I have an image that's upright or inverted. So if the magnification is positive, then I have to have an upright image. If the magnification is negative, then that means I have an inverted image. So we'll be able to make, we'll basically be able to use our two equations to calculate the object distance, image distance, focal length. One of those is unknowns. We'll be able to calculate the magnification. And then what we'll be able to do is think about what those values are to determine whether we have an image that's real or virtual, enlarged or reduced, or upright or inverted.